Welcome to the portion of the lecture on Python programming fundamentals about iteration. In a previous example on functions, we repeatedly called a function on a variety of inputs. We had do it 1, 2, 3, 4, 5, 6, 7, 8, 9. The function was useful for packaging the code in a way that let us use it over and over again. We could easily modify that code once to modify its application anywhere else in our program. However, we still had to write out the function call many times as we changed the input. Iteration is useful when we want to perform one task over and over again, as we did here. Again, iteration, this idea that we're introducing has a kind of normal expression in common English. We might say, for instance, that as long as I live, I will drink water. While I live, I will drink water. Or for as long as I live, I will drink water. Often, when we want to do something over and over again, we'll express it as a while loop or a for loop. While some condition is true, we will do something. Or for some set of values or for some duration of time, we will do something. Let's look at an example of iteration in code. So we'll begin with while loops. A while loop continues to evaluate while some condition is true. So if we begin with x equals 0 and say while x is less than 5, we'll do whatever is in the body of the while loop so long as x is less than 5. We have to be careful to make sure that x eventually becomes greater than 5, or else we'll get stuck in an infinite loop. Fortunately, in the body of our function, we increment x by 1 each time the loop executes. Therefore, the result of this loop is to print x from while it has the values 0 through 4. Once x attains the value 5, the while loop halts because this condition becomes false. Evaluating this code, or executing this cell, we see 0, 1, 2, 3, 4, where x was printed out before it became 5. In fact, if we evaluate x, we find it has the value 5 now. Often, we won't, especially when we're working with data, we won't want to do something while some condition is true, but we'll want to do something for every data point in our data structure. So more often, we'll iterate using for loops instead of while loops. However, let's examine a more realistic example, or a more complex example, using a while loop. One example of an iterative process is the Fibonacci sequence. In order to calculate the numbers in the Fibonacci sequence, we need to calculate the earlier numbers in the Fibonacci sequence. Therefore, we can only calculate the nth number by iterating forward from the first number in the sequence. Here we define a function to calculate the numbers of the Fibonacci sequence. This will print out the first n numbers in the Fibonacci sequence. we begin by initializing the first two numbers in the sequence, as well as a count to index which number we've reached in the sequence. We'll print out the first two numbers, and then while the count is less than n, the point at which we'll terminate the sequence, we calculate the next number, print it out, and update where we are in the sequence. We additionally update our count, or index, of which number we've printed out. We also have a version for printing out the Fibonacci numbers below some number x. This function takes a similar form to what we had seen before, but shows a different case of creating a condition within the while loop. Again, we initialize our sequence. We then test if we've already exceeded x. If we haven't, then we print out the numbers. Then, so long as the next number is less than x, this is the value of the next number, we calculate the next number, we print it out, and we update the previous two numbers in the sequence. Let's see these functions in action. If we want the first 7 Fibonacci numbers, we can print out or evaluate first n Fibonacci on the value 7. 1, 2, 3, 4, 5, 6, 7, 8. Well, here we have an off by 1 error, which is a common kind of error in programming. And maybe, depending on how you define the Fibonacci sequence, this is maybe not the first number, but the 0th number, and then this is the first number. I'm not going to worry about this too much. Though it is a good point at which for me to emphasize that often when we're writing iterative loops, whether they be for loops or while loops, we have to beware of off by 1 errors, where we do something one more time than we want, or one less time than we want. Similarly, if we want the Fibonacci numbers below 40, we can evaluate below x Fibonacci on the value 40. And here we have all the Fibonacci numbers up to 40. We can see 34 plus 21 would give us 55, which would be larger than 40. So our loop stopped. Now, as I mentioned, often when we're working with data especially, we will want our program, instead of performing an action while some condition is true, to perform an action for each element in a data structure. One example is we could write a program that prints out cooking instructions. We would begin with a list of instructions for cooking something. Here's a list of instructions for making bread, for example. And then we might want to iterate through this list and simply print out the instructions one by one. We could maybe prompt the user to enter whether or not they have finished the step and are ready to continue to the next. In order to illustrate this, we have to introduce Python list, which is a data structure that represents a list. We'll talk more about lists in a subsequent lecture, but for now, we'll just create one. So bread recipe is a variable that contains a list of instructions for making bread. We'll also make a soup recipe and a beans recipe, which will have their own lists of instructions. The instructions are just strings of text. Now, we could use a while loop to iterate through these instructions, and while there are instructions left, we could print them out. But a more direct way to do it is to say, for each instruction in our list, print out that instruction. And that's exactly what we'll do. We'll define a function, printRecipe, which accepts some list of instructions. And for each step in the instructions, we'll print out that step. And we see, if we print out the soup recipe, we get a nice printed list of those instructions. Likewise, for the bread recipe and the beans recipe. Notice, despite the fact that each recipe was different lengths, this short function was able to appropriately stop when it hit the end of the instructions. A for loop works in the following way. We define a iterating variable that will take on the values one by one of the contents of some iterable, something that we can iterate over. So when we call printRecipe on soup recipe, that list gets passed in as the instructions argument. Step then takes on the values in that list one by one as we perform the action in the body of the loop. So first step gets set equal to dissolve salt in water, and we print out that step. Then the body completes and we iterate to the next element in the loop. Boil water. Step becomes boil water and we print out that step. And so on. Add bones to boiling water, chop onions, chop garlic, etc. Step takes on each of these values as it iterates through instructions. We can iterate over a variety of data structures in Python. We'll talk more about data structures in a later lecture. We can even use a for loop to encapsulate the do-it example that we had before. I can create a list of the numbers 1 through 9, and I can say for n in this list, do it n. And we see the do it function gets applied to n as n iterates through all the values in this list. Let's now revisit the Fibonacci sequence function, but compare a implementation using a while loop and an implementation using a for loop. This is the first n Fibonacci function we saw earlier using a while loop. In contrast, here is an implementation using a for loop. This for loop uses a new command that we haven't seen before called range. Range generates numbers between the first argument and the second argument. Or, if we don't supply two arguments, it will generate numbers between 0 and the first argument. We'll talk about range more in the future, but if you play around with it, you can get a pretty good idea of how it works. Range 10 returns the numbers 0 through 9. Range 1 through 10 returns the numbers 1 through 9. And range 1, 10, 2 returns the numbers 1 through 9, counting by 2s. Here, we're using it to iterate starting at the second number of the Fibonacci sequence and go up to the nth number. We can see these two implementations return the same results. As an exercise, I'd like you to compare these two implementations and think about them. Consider them. Argue with yourself about which one is better, the while implementation or the for loop implementation. I'm going to go to the discussion board and create a new question asking which is better. So I'll create a question. And as I'm creating this, I'm going to use code formatting by enclosing these names, which are code, in backticks. For more information about how to create and answer questions on the discussion board, watch the introductory video for the course. It's important that we conform to good standards when using the discussion board for it to be a useful resource to all the students, as well as to me for conducting office hours. I'm also going to include the implementations as a reference. And by highlighting all of this and then clicking the code button, all of that code gets formatted as a code block. Finally, I'll tag the question with program flow, iteration, Fibonacci, and exercise. So I invite you to answer this question with your own thoughts as a response to this exercise. I'm not going to take time at this point to talk about recursion, but you can read this section on your own. Recursion is similar to iteration, but instead of repeating a task over and over again based on some condition, like a while loop, or based on iterating through some data structure, like a for loop, recursion accomplishes repetition by having a function call itself. Recursion is a topic that often takes a lot of study and practice to get used to. If you're interested in it, you can ask more about it on the discussion board or search the internet for more about it. But there's a brief section here that you can study on your own. I'd like to conclude this group of lectures by talking about putting together all the things we've learned and exploring a bit of a more complicated set of functions that work together. We began this set of lectures by talking about programs as a list of instructions that can build up to a complex hierarchy of functions and variables that interact to perform some complex task out of using simpler tasks as building blocks. That's what we're going to do now, using conditionals, iteration, variables, and functions. In this example, we're going to write two functions that will work together to print out prime numbers. Prime numbers are important in computer science for purposes of cryptography, so people have thought quite a bit about how to compute prime numbers, and people have also thought a lot about their mathematical properties, which makes them a frequent topic of computer science exercises or programming exercises. So here, we'd like to print out prime numbers up to some number n. In order to do that, we're going to write a helper function that checks if some number is prime. So first, we'll define an isPrime function that accepts a number as an argument. Now we need to consider several cases. First of all, we know prime numbers are divisible only by 1 and themselves. 1, by special definition, is not prime. So if our number is equal to 1, we'll return false, because 1 is not prime. For any number greater than 1, we need to check if any number between 2 and the number itself is capable of evenly dividing the number. So, for each possible factor between 2 and the number itself, we'll check if the number can be evenly divided by the factor. If it can, then that number is not prime, so we'll return false. Once we've iterated over all the possible factors that could possibly evenly divide the number, then we know that no factor evenly divided it. Because if it had, we would have already returned outside of this function. Therefore, once this iteration is complete, we know we've found a prime number, and we can return true. To print out the prime numbers up to some number n, we'll start at the number 1 and iterate up to the number n. For each number in this range, we'll check if the number is prime. If it is prime, we'll print out that that number is prime. This is another method of string interpolation. It's an older style, but it also works. So we'll define these functions, and if we call print primes on 42, we get all the prime numbers up to 42. So 2 is prime, 3 is prime, 5 is prime, 7, 11, etc. These two functions exhibit some amount of that hierarchy or modular idea that I mentioned earlier. Because the print primes function is trying to accomplish a somewhat complex task, we've captured some of that task in this simpler isPrime function. IsPrime accomplishes a sub-task or sub-process of the print primes task. So we simplify the print primes function conceptually by defining a meaningfully named function isPrime. Then the print primes function is very easy to read and understand. For each number between 1 and n, if that number is prime, print it out. We don't have to think as hard when reading through the print primes function, because a lot of the functionality is captured in this isPrime function. As mentioned before, we might use a function to perform a task many times. For instance, we iterated doIt over the numbers 1 through 9. Here, we show a slightly more complex example of a similar idea. We have a list of numbers between 0 and 19. If we wanted to create a list of the prime numbers 0 through 19, we could create an empty list called prime list. Then, for each number in our list of numbers, if the number is prime, this is not going to do quite what I want. I'm going to rewrite this very slightly. So if the number is prime, we'll append the number to our list. And now we have a nice list of primes. Unfortunately, since we had a small oversight in our isPrime function, which led 0 to be included as well. Why don't we go back and revise our function to say if number is less than 2, it's prime. Now, 0 won't be included in our primes list. Another method of iteration is what's called a comprehension. This is a special feature of Python that is very useful and that we will revisit in the subsequent data structures lecture. Comprehensions allow us to construct data structures as we iterate. So this is what's called a list comprehension, because it's going to return a list. And we know that because this is enclosed in square brackets. Again, we'll review this concept after we talk about the list data structure. But you can see this is a one-line for loop. We're going to return number for each number in the list of numbers if that number is prime. This might be a little confusing at the moment, but don't worry, we'll come back to it in a future lecture. In any case, we can see that this has the same result as the more verbose implementation above. You may have noticed over the course of this notebook that we had functions that some of them accepted input, some of them didn't. Some of them accepted multiple inputs, like test high score. Remember, arguments are just placeholders for input. We can have many or we can have few. However, those arguments are not related to things outside the function. However, one thing we have to be careful about is we may define functions that use names that are defined outside the function and aren't defined inside the function. So in this example, we have a function defined with an argument a, and that function prints the value of the argument. If we set a to be equal to 5 and then print this 2, the function prints 2. A is not affected by the argument a. On the other hand, if we define a function with no argument, and then inside the argument or function we print a, this function body doesn't have any definition for the name a contained within it. Therefore, the function will go looking outside of itself for meaning for this name. In other words, it will look into the global scope for a name A. The printIt function will print the value of A defined outside the function. Again, it can take time to get used to this idea of scope. But basically, so long as a name is defined inside of a function as an argument or in the body, the function will use the name found inside the scope of the function. If there's no definition for a name inside the scope of a function, it will look for a definition outside the scope of the function. This idea can be built upon using what's called function closures. This is an advanced topic that I won't discuss in this video, but you can read about in this notebook and practice with on your own time. Additionally, we can use some tricks with arguments, such as default arguments. In this print_to_do function, we have 4 arguments. And if we want to run the function, we need to supply all 4. If we don't supply all 4, for instance, if we only supply 3, we hit a type error. Print_to_do is missing one required positional argument, sleep. In other words, we supplied the arguments watch TV, read, and eat, but the function requires sleep as well, and we didn't supply that argument when we called it. One way to get around this is to supply what are called default arguments, or default values for the arguments. In the function definition, we can have an argument equal some value. If we don't supply an argument when we call the function, then these arguments will automatically take on these values. So in this case, I can safely call this function with only 2 arguments, watch TV and read. The other arguments will automatically be set to true by default. And we see this result from calling the function is the same as when we called it with all trues. Another trick that we can use with functions is to allow for variable amounts of arguments. We can do this by putting star args in the space for arguments in the function definition. Star args will function as a iterable within the function. So we can, for instance, iterate over the arguments supplied to the function and print them out. For this function, we can supply as many to-dos as we want as arguments. If I specify only 2, then it will print out those 2 arguments by iterating over them. If I supply more, it's able to adjust to those additional arguments. Note, down here I have some topics that were used throughout this notebook that I only briefly touched on and that are not documented in this notebook in any way. But they are called out here if you would like to read further about them. That concludes our discussion of Python programming fundamentals and program flow. This notebook has been called Program Flow because it describes how we can use conditionals and iterations to control the order in which instructions are executed and direct our kind of code in different directions depending on the value of different variables or data structures. In the next lecture, we'll be discussing data structures.